In this section, we're going to look at linear inequalities in one variable, and we have all the same properties we had when we solved equations. The only difference will be in the multiplication property. With inequalities, anytime we multiply or divide both sides of an inequality by a negative number, we have to, at the same time, reverse the direction of the inequality. You'll see as we work our first example. Let's take a look. So I want to solve negative 2x plus 1 is less than 7. So I'm going to use my addition property to add negative 1 to both sides of the inequality to go on my way to isolating the variable x. So when I do that, I'll have negative 2x less than negative 1 plus 0 is 0, and 7 plus negative 1 will be 6. Now at this point, I want to multiply both sides by a negative 1/2, so I have just x left on the left side. So I'll do that, negative 1/2 times negative 2x, and at the same time I do that, I want to reverse the direction of the inequality symbol. Whoops. So now it's going to point to the right instead of to the left. I multiply one side by negative 1/2, I have to do the same thing to the other side. So you can see here's the difference between solving equations and solving inequalities. I can multiply both sides by a negative number anytime I want. It's just that when I do that, I have to also at the same time reverse the direction of the inequality symbol to keep this a true statement. Here it pointed to the left, now it points to the right because I multiplied both sides by a negative 1/2. Let's continue the solution. Negative 1/2 times negative 2 is 1, times x is just x, greater than negative 1/2 times 6 is negative 3. Now, here's my solution. X is greater than negative 3. The next thing I want to do is graph this solution. So what I'm going to do is get a visual representation of the solution to this inequality. One way to do that is with the real number line. Let's see, I'm running out of ink here. I'll draw a real number line. I'll put in 0 for reference, and I'll put in negative 3 because that's the endpoint for my inequality. Now, I want a picture of all the real numbers that are greater than negative 3 on the number line. If you just took an elementary algebra class, you may have done the graphs like this, where we draw a circle around negative 3 and leave it open to show that negative 3 is not part of the solution, and then we draw an arrow showing the region of the number line where we have the numbers that are greater than negative 3. So it looks like this. Now I want to go a little farther with this and use what's called interval notation. So I'm going to use a kind of symbolic notation to represent the same solution set, and it looks like this. I'm going to use an open parenthesis here at negative 3 to show that negative 3 is the end point, but it's not included in the solution set, comma, and then I want to go all the way out to infinity. So what this represents is all the numbers on the number line starting with negative 3 but not including negative 3 and going all the way out to infinity, just like this graph right here does the same thing. So this is a visual representation. Here's some notation that means the same thing. Now I want to show you the kind of graphs that we're going to use in this book. You may have done this in elementary algebra. Now in intermediate, we're going to look at the graphs this way. I'll draw my number line again. I have negative 3 for the endpoint and 0 again for reference. But this time, instead of drawing an open circle at negative 3, I'm going to use my open bracket like this, color in all the numbers up above. Looks like that. And so this represents all the numbers on the number line from -3 on, but not including -3. Now in the next example we'll see what this looks like when the endpoint is included. Let's take a look at that example. In this case we have 1/2 greater than or equal to -1/6 minus 2/9 times x. Okay, in this case I think I want to start by getting rid of these denominators. I'm going to look for the least common denominator for 2, 6, and 9 and multiply both sides of this equation by it just to simplify. That least common denominator is 18, so I'm going to multiply this side by 18, and I'm going to multiply this side of the equation by 18. Now, 18 is a positive number, so I don't have to worry about reversing the direction of the inequality symbol. Anytime I multiply both sides by a positive number or divide both sides by a positive number, the inequality always points in the same direction it was pointing. Let's continue. 18 times 1/2 is going to be 9. Greater than or equal to, now 18 times -1/6 will be -3. 18 times 2/9, 9 will divide into 18 twice, times 2 is 4, times x is 4x. So now I have 9 greater than or equal to -3 minus 4x. I'll add +3 to both sides, so I'll have 12 greater than or equal to negative 4x. Now I'm in that situation again where I have to multiply both sides by a negative number. I want to isolate x on this side, so I'm going to multiply both sides by negative 1/4. Let's take a look. I'm going to multiply both sides by negative 1/4, and at the same time I'm going to reverse the direction of the inequality symbol. So negative 1/4 times 12. Instead of greater than or equal to, I'm going to reverse this, and it will be less than or equal to negative 1/4 times negative 4x. Negative 1/4 times 12 will be negative 3, less than or equal to negative 1/4 times negative 4 is 1, times x is x. So here's my solution written with an inequality, negative 3 less than or equal to x. I want to graph the solution, so I'll draw my number line. I'll put in negative 3 for the endpoint. I'll put in 0 for reference. I want all the values of x that are greater than negative 3. Remember, the inequality symbol points to the smaller number, so x is the larger number between negative 3 and x. Since negative 3 is included in the solution set, I'm going to use a brace like this that shows that it's included. And so we go in this direction, and there's the solution written graphically using my number line. Next thing I want to do is write the solution using interval notation. With interval notation, I'm going to use my same bracket here. This shows me that the solution starts at negative 3, includes negative 3, and then goes all the way out to positive infinity. Positive infinity we always use with an open bracket or brace like this. So negative 3 to infinity, that's my interval notation for this solution set. So you can see I use these closed brackets like this and the open sort of parenthesis when I'm using for my endpoints to show whether they're included in the solution or not. Let's take a look at some more of these graphs and the corresponding interval notation. Here I have written the inequality x is less than 2. Here's its corresponding graph. Notice that I've used the open parenthesis here showing that 2 is not part of the solution set, and it opens in the same direction that the graph is going. Here I have the same thing written with interval notation that says this is the set of numbers on the number line that come up from negative infinity to 2 but don't include the number 2. By contrast then, here's the inequality x is less than or equal to 2. Notice how I write that graph with the brace right here, the bracket, and it points in the same direction that the graph goes. This tells me that the number 2 is included in the solution set, and then the corresponding use of interval notation for the same set, the set of all real numbers x that come up from negative infinity, stop at 2, and include the number 2. Okay, so that's the connection between our inequalities, their graphs, and interval notation. Let's continue to work on these linear inequalities. For my next example here, I have what's called a compound inequality. It's two simple inequalities here connected with the word or. So all I want to do is graph the solution set to this whole compound inequality. What I'm going to do first is graph this solution set, and then I'm going to graph this solution set, and I'm going to see then how to connect them with the word or. So x is less than negative 2. I'll just draw a number line in, put in 0 for reference. Here's negative 2. X is less than negative 2. So that graph looks like this. Okay, I want to connect this graph with the word or to the graph of x is greater than or equal to 5. So I'll graph this one on another number line, just so we can take a look at them separately. Here's 0. Here's 5. Greater than or equal to 5. Use my bracket here, and that graph goes to the right. So where are all the numbers on the number line that do this or do this? Well, when I say the word or, I'm talking about the union of these two graphs. So I want everything that's on either one of the graphs. So anything over here works, and anything over here works. So it's really the union of these two. I put them together. All the numbers on the number line that are either less than negative 2 or greater than or equal to 5 will look like this. It's down in this region together with the numbers up in this region. Now, to write this with interval notation, I'm going to have to take two little intervals and connect them with my union symbol. So to write this with interval notation, I'll come up from negative infinity to negative 2, but I won't include negative 2. I want the union of that with The set that starts at 5 includes 5 and goes off to positive infinity. So here's my interval notation that represents the same set of numbers on the number line that this graph represents. When I have two inequalities here connected with the word or, that's called a compound inequality. Let's see what happens when we have two inequalities connected with the word and. That would be problem number 4, where I have x is greater than or equal to -4 and x is less than 7. So here I have one inequality, a second inequality, they're connected with the word and. So on the number line, I want to find all the numbers that do this and do this. That's different than all the numbers that do one or the other. So let's use our same procedure, though, and graph this inequality. Let's see, I'll put in 0 for reference, -4. I want x greater than or equal to -4. So from here all the way out here. So let's graph that this way. So here's my solution set for my first inequality. X is greater than or equal to -4. So from -4 all the way on out. Now I want to connect that with the word and to the graph of x is less than 7. So I'll draw number line again, put in 0, here's 7, and I want to graph all the numbers on the number line that are less than 7. So it won't include 7. I'll use my parenthesis. Goes down this way. Now, as you look at this, ask yourself, where are all the numbers on the number line that do this and also do this? So I want the intersection of these two sets. I want the numbers that are both greater than -4 and at the same time less than 7. Well, that's going to have to be the numbers that start at -4, include -4, and go up to 7, but don't include 7. Here are all the numbers on the number line that do both this and this. So this comes out to be what's called also a continued inequality when I write it with my inequality notation. So I can shorten things a little bit here. This looks like x must be a number between -4 and 7, including -4 but not including 7. I can write that with inequality notation this way. -4 less than or equal to x less than 7. Here's what's called a continued inequality that represents this set right here. Here it looks like x is between -4 and 7, and sure enough, with this notation, x is between -4 and 7. Now, if I also want to write this using interval notation, it's very simple. I'll use a bracket right here for -4, showing that -4 is included, comma. I want to start at -4, include -4, and go up to 7 and stop, but not include 7. So there's my interval notation that's equivalent to this inequality, that's equivalent to this graph. Let's try one more example. We have another continued inequality, a little more complicated here, and we're going to have to extend our rules that we use, and we'll just say this. Anything that we do to one of these three expressions, we have to do to the other two also. What I want to do is isolate this variable a between these two inequality symbols. I'll start by adding -20 to the center expression so that I'll have just 40a left. If I do this to the center expression, I've got to do it to the two outside expressions also. Now remember, this is just a shorthand notation for the addition property for inequalities. I'm really adding -20 to each of these three expressions. I know it won't change the solution to this inequality. So -80 now is less than 40a, which is less than 40. So I've added -20 to each of the three expressions. I end up with this inequality. I'm still trying to isolate a between the two inequality symbols. So what I'm going to do is divide all three members by +40. Now, since 40 is a positive number, I don't have to worry about reversing the direction of the inequality symbols. So let's just do that. I'll divide that by 40, this by 40, and this by 40. So when I do that, I end up with -80 divided by 40, which is -2. So I have -2 less than a less than 1. Nice simple continued inequality. I'm going to draw the graph of this inequality next. Here I have -2. I have 1. It doesn't include either endpoint, so I'm going to use my open parentheses like this. Color in the numbers in between. And there's the graph of the solution to this continued inequality. Now, all I had to do was extend my properties to say that whatever I do to one of these three expressions here, I do to the other ones. So I added negative 20 to all three expressions. That's okay. It's just an extension of the addition property of inequalities. Then I divided all three members by 40, another extension of the multiplication property. 40 is a positive number, so I don't have to worry about the direction these inequality symbols point in. Here's my final inequality right here. I want to graph the solution set. It looks like this. One more thing. I want to write this with interval notation. With interval notation, pretty simple. Starts at negative 2, but doesn't include negative 2. Goes up to 1, but doesn't include 1. So with interval notation, it looks like this, negative 2 to 1. So that's a look at solving some linear inequalities in one variable.